Okay, in the previous class, we have discussed about how to compute the response of an LTI system using convolution, and we have got an important relation that if you pass a sequence xn through a system which has impulse response hn, the output yn is nothing but the convolution of xn with hn. Okay, and yn was given by this equation. This equation is termed as convolution sum. Okay, if it is a continuous time system, you will get integral in terms of summation. In that case, it becomes yt is equal to integration of x tau h of t minus tau d tau. This is called convolution integral. Okay, so if you know the impulse response of the system, you can find the output using the convolution of input signal and the impulse response. Okay, now there are certain properties of convolution. The first is commutative. Okay, so by commutative property, it simply means that the convolution of xn with hn is same as the convolution of hn with xn. Okay, and you can simply prove this. If I take convolution of xn with hn, it was summation of x of k h of n minus k from minus to plus infinity. In this equation, if I change this summation from k to r, where r is equal to n minus suppose k, I can write it as x of k. Now k from this will become n minus r into h of n minus k will become r, and the summation of r will be again from minus to plus infinity. Okay, or you can write it as summation of h of r x of n minus r from minus to plus infinity. Okay, so this is nothing but h of n convolved with x of n. Okay, it means either you find the convolution of xn with hn or hn with xn, you are getting the same output. So what it means, if you have a input xn and the impulse response is hn, you are getting output yn. In place of this, if you take input as hn and the impulse response as xn, you will again get the same output. Okay, so the role of input and the impulse response can be interchanged. This is what is the commutative property. So either xn can be taken as input and hn as the impulse response, or hn can be taken as the input and xn can be taken as the impulse response of the system. You are going to get the same output. Then the second property is associative. So by associative property, we means that convolution of xn with h1n plus h2n is equal to xn convolution h1 plus xn convolution with h2n. Okay, this is just like this: a into b plus c is equal to ab plus ac. This is what is associative property in number system. Okay, So if you interpret this equation, what you see in the left hand side, you are finding the convolution of xn with h1n plus h2n. Okay, it means you can say that xn is the input and the response of the system is h1n plus h2n. The output of this is your left hand side. Okay, on the right hand side, what you are doing, you are first finding the convolution of xn with h1n. It means you are passing xn through a system with impulse response hn, you are getting this output. Then the second part is the same input, it is passed through a system with impulse response h2n. Okay, and then you are adding them together. This is your right hand side, and both of these are equal. So what it states, now in this case, these two systems, they are basically in parallel, h1 and h2n, and this system can be replaced with this system. Okay, it means if two systems are in parallel, okay, their impulse responses are added together. This is what is associative property. Okay, so parallel system means both the systems have the same input and their outputs are added together. This is what is called as a parallel system. So if you connect two systems in parallel, to find the overall response of the system, you have to simply add their individual impulse responses. This is associative property. And the third one is distributive, okay, which says that xn convolution with h1n convolution with h2n is equal to xn convolution with h1n, then convolution of this with h2n. Okay, again, if you interpret this equation, on the left hand side you have a system with input xn and the response is h1n convolution with h2n. Okay, on the right hand side you have first xn convolved with h1n. It means you have an input xn, pass it through a system with response h1n, you are getting this output, and this is again convolved with h2n. It means this output is given input to a system which has an impulse response h2n. So this is again passed through another system which has a response h2n, and the output of this is your right hand side of this equation. So these two systems again are equivalent. So what you can conclude here is that now in this case h1 and h2n, they are connected in cascade. Okay, means output of one is given as input to another system, and when the two systems they are connected in cascade, what you see in the overall response, the overall response of the system is nothing but the convolution of individual responses, convolution of two impulse responses. Okay, so if two systems are connected in cascade, they can be replaced with a single system where the impulse response of the system is nothing but the convolution of the two impulse responses. It is not multiplication. Okay, mind it. When you see in the Z transform or in the Fourier transform, the convolution becomes multiplication there. okay, but in time it is convolution. So these three properties: commutative, where the role of input and the impulse response can be interchanged. Second is associative, which states that if the systems are connected in parallel, their impulse responses added together. And the third one is distributive, which states that if the systems are connected in cascade, the overall response of the system is the convolution of their individual responses. Okay. Now these linear time invariant systems that we have discussed, we have discussed some other properties of systems, which was apart from this, apart from linearity and time invariance, there was system with or without memory or a memoryless system. Then we have studied what is a invertible system, then what is a causal system, and then a stable system. Again, then linear system and time invariant system. Of course, these two properties, they are included here in LTI systems. Okay. Now if the system is linear and time invariant, it is basically characterized by its impulse response h of n, and you will see that by looking at the impulse response of the system, if the system is linear and time invariant, you can have an idea about whether the system is going to be memoryless, or it is going to be invertible, or causal, or stable. Okay. If I take the first case, memoryless, whether a LTI system will be memoryless or not, how you can check from its impulse response. Okay. Memoryless system, we have defined a system in which the output of the system at any time, it depends upon input at that time only. Now if the system is already linear and time invariant, it means its output can be expressed as the convolution, that is x of k h of n minus k, or since it is a commutative property, I can write it as h of k into x of n minus k summation over k. Okay. Now if the system is to be memoryless, it means the output y at any time n, it should depend upon input at that time only. But if you see this equation, it contains the present input, the past input, as well as the future input values. Because if you expand this equation, you are going to get h0 into xn, then h1 into x of n minus 1, and so on, and similarly h of minus 1, x of n plus 1, and so on. Okay. So this is the present input xn. X of n minus 1 is your past input, x of n plus 1 is your future input, and so on. So if the system is memoryless, it means all these terms, they must be set to 0. It should only depend upon xn. It means only this term should be present in this equation. So for all these terms to be 0, your h of 1, h of 2, h of minus 1, h of minus 2, everything should be 0. It means the impulse response of the system should have only one sample, that is h of 0. Okay, because all other samples, they give you the present and the present not present, the past and the future values of the input. So for a memoryless system, all these values should be 0. It means your h of n should be in the form of k delta n. Okay, it should have only one sample at n is equal to 0, and this sample can be take any value k. This is what is h of n. If any system has an impulse response like this, that system will be a memoryless system. Sorry. Okay. If it contains more than one sample at n is equal to 0, it will not be a memoryless system. Okay. Then similarly you can take causal systems. Now we assume that the system is already LTI system. Okay. And how to check its causality? So causal system means that the output at any time, it depends only on the present input or the past input. It should not depend upon the future inputs. This is what is a causal system. Again you can say what should be the condition for causality. Yn is equal to xk h of n minus k, or you can take it as h of k x of n minus k. Okay, so you'll get h of 0 x of n plus h of 1 x of n minus 1, then h of 2 x of n minus 2, and so on, then h of minus 1 x of n plus 1, and so on. Now for the system to be causal, it should depend upon the present input, that is xn, or past input, that it can may contain x of n minus 1 or x of n minus 2, x of n minus 3, but it should not contain x of n plus 1, which is the future value. Okay, it means that h of minus 1, h of minus 2, h of minus 3, everything should be 0 for n less than 0. So your impulse response should be basically 0 for n less than 0. This is what is the condition for a system to be causal. If its impulse response is not 0 for n less than 0, you are going to get the future values of the output in this equation of convolution. So as a result, this system will become non-causal. Okay, so if I take an impulse response like this, if this is the impulse response of an LTI system, and you have to state whether this system is memoryless or causal. This is not memoryless, because for this system to be memoryless, it must have only one pulse, that is at n is equal to 0. Okay, so this system is not memoryless. What about the causality? The impulse response should be 0 for n less than 0, but it is not 0. It has two non-zero samples for n less than 0. So as a result, this system is non-causal. Okay, so for causal systems, for n less than 0, the entire impulse response should be 0. Then only the system is causal. And similarly, you have invertible. If you say invertible system, so how we have defined invertible system? A system in which distinct inputs they generate distinct outputs, or you can say that if you give xn as input to a system which has some impulse response hn, if I can pass this system through another system which has impulses, suppose this is h1, another system h2n, the output should be same as xn. It means these two systems, they are in cascade, and their net response should be equal to, the output of this should be equal to xn. Now since these two systems are in cascade, I can replace them with a single system where the impulse response will be the convolution of h1 and h2n, and this should be same as xn, and this will be equal to xn only when this should be equal to delta n, because the convolution of xn with delta n is xn. Okay, so this is the condition for invertibility. So for any system h1n, if you can find a system, this is h2n, sorry, if you can find a system h2n so that the convolution of these two is equal to the impulse signal, then this h2n will become the inverse of h1n. Okay, like suppose if I take a simple example, you have a system yn is equal to x of n minus n naught. Okay, what is the impulse response of the system? Hn. If your input is delta n, yn is hn. So if I take x as delta n, your hn will become delta n minus n naught. Okay, so it is a time shift by n naught. If I again shift this signal by n naught to the left, I will again get xn. It means for this system, if I define a system with the impulse response delta n plus n naught, so the convolution of these two, hn convolved with h1n, that is delta n minus n naught convolution with delta n plus n naught. This is nothing but delta n. So h1n, which is delta n plus n naught, is nothing but the inverse of hn, which is delta n minus n naught. Okay, and this convolution of these two is delta n. I hope you understand this, because see, the convolution of xn with delta n is nothing but xn. The convolution of xn with delta n minus k is nothing but x of n minus k. So in this case, if I take this signal as suppose xn, so xn convolved with delta n plus n naught, with delta n plus n naught, it is nothing but x of n plus n naught. And what is my xn? Xn is nothing but delta n minus n naught, so it will become delta n minus n naught plus n naught. You will get delta n as the output. Okay, this is how you define invertible systems if they are LTI. And then finally you have stability. For the stability, we define bounded input, bounded output. Okay, it means for any system, if you give a finite input, if for that you are getting a finite output or a bounded output, we say the system is stable. Okay, so again here yn, which is summation of hk x of n minus k for a LTI system. Okay, let us assume that your input is finite. It means the magnitude of x of n is less than b for all n. Okay, your input is bounded. For any value of n, the magnitude of xn is less than b. So what will be the magnitude of yn? The magnitude of yn will be equal to mod of h of k x of n minus k. And you can write this equation as less or equal to summation k from minus to plus infinity mod of h of k into mod of x of n minus k. Okay, I hope you can understand this. It means the magnitude of sum of products is less than equal to sum of their product of the magnitudes. It is like this. Suppose you take magnitude of minus 2 plus 4 plus 5. this should be less than or equal to always magnitude of -2 plus magnitude of 4 plus magnitude of 5, isn't it? This is what I have used here. Okay, because in this you are taking the magnitude of the sum. In this case you are taking the sum of the magnitudes. So when you take the sum of magnitudes, all the negative values will become positive. So this will always be greater than this. Okay, and now see, I can write it as, since x of n minus k, magnitude of x of n minus k is less than b for all values of n and k. Okay, so I can write this as less than b summation of hk k from minus infinity to plus infinity mod of this. Okay, why I have written this equation like this? Because see, we have assumed that magnitude of xn, it may be x0, x1, x2, anything. So n minus k, it can be x0, x1, anything for any value of n and k. It is going to be one of the samples. Okay, its maximum value is b. Okay, it means when you find this product, again I take the example to simplify this. Suppose you have mod of h of k, which can take any value, and then here this mod of x of n minus k. So x of n minus k, for one value of n and k, it may be supposed 2. Okay, then for other value mod of h of k, for other value it may be 3, it may be maybe 4 or 5, but it will take a maximum value. Suppose that maximum value is 7. Okay, and when I have written this equation in the form of this, I have assumed that all these factors, they are basically 7. Then only I can get b as common. It means this will be less than equal to always 7 into mod of hk summation, isn't it? Because in this case you are multiplying with the factors and adding them together. These factors, they may have different values, but what is the maximum possible value? That is b. So if I assume that each value is b, this entire summation must be less than this summation. This is what we have done here. Okay, so if your input is finite, bounded, now your output will be bounded if this summation will be less than infinity. Okay, it means for the system to be stable, your mod of hk k from -2 plus infinity should be less than infinity. It should be finite, or you can say that the impulse response of the system must be absolutely summable. Okay, if you go in the continuous time, it is like this. Your h of t dt, the impulse response should be absolutely integrable in that case. So if the impulse response is summable, your system becomes stable. If it is not summable, your system becomes unstable. Okay, this is very basic criteria for stability, and you will see that when we discuss in the Z transform, you might have studied earlier. For a system to be stable, we say that all the poles, they must lie inside the unit circle. Okay, this is a circle of unit radius. All the poles, they must inside the unit circle for the system to be stable. And why we say this thing? And similar in the Laplace, if you see, or this is not in fact the general case of stability. The general case for stability in the Z transform is that this unit circle it must lie in the region of convergence, or in the Laplace domain. When you say this is sigma j omega axis, the imaginary axis, it must lie in the ROC for a system to be stable. Okay, we will discuss again this, but I'm just taking how it is related to this. See, for this case, if the unit circle lies in the ROC, the region of convergence is basically that set of points in the Z plane where the Z transform takes a finite value. Okay, and if the unit circle lies in the Z transform, when you see that relation between the Z and the Fourier transform, you will see that on the unit circle your Z transform becomes Fourier transform. Okay, similarly in the Laplace transform, on the imaginary axis the Laplace transform converges to Fourier transform. Okay, now if I am saying that the unit circle is in the ROC, it means I can find the Z transform of this signal on the unit circle. If I can find the Z transform of the signal on the unit circle, it means I can find its Fourier transform. And for finding the Fourier transform, there are some conditions. The first condition is that this signal must be summable. There are conditions which is called as Dirichlet conditions that we will discuss. So you can find the Fourier transform of any signal which is absolutely summable. Okay, it means if I am saying for any system the region of convergence is in the unit circle lies in the ROC, what it basically means, I can calculate the Fourier transform, and if I can calculate the Fourier transform, it simply means it follows the Dirichlet conditions, or you can say that its impulse response is absolutely summable, so the system becomes stable. Okay, this is how you see the stability in the Z domain, or similarly how you see the stability in the Laplace domain. We just look at the imaginary axis. If the imaginary axis lies in the region of convergence, the system becomes stable, otherwise it is unstable. Okay, so I will give a question for this lecture. Suppose you have two systems which are connected in cascade. You have to find their impulse response. Okay, yes, let me give an example. So two systems which has impulse response h1n is equal to 1 between 0 and 4, otherwise 0, and h2n is equal to alpha raised to power n between 0 and 6, otherwise 0. Okay, the two systems are connected in cascade. First part, they are connected in cascade, so find the overall response of system. And the second case, if they are connected in parallel, what will be the overall response of the system? Okay, so for cascade, you know, it is the convolution of the two. For parallel, it is simply the addition of the two. So in this case, you have to find the convolution of h1n with h2n. In the second case, you have to simply add the two responses. You will get the overall response. Okay. Thank you.